Welcome to our 102 class, and what we're going to do here is going to be really far away from our planet. The 101 class is solar system astronomy. The 102 class gets outside the solar system. You don't need to have any prior information on the solar system to make it through this class, but this first lecture I'm going to go through some open basic kinds of concepts so that you can sort of get into the swing of things astronomically. A couple of things to pay attention to. In the files, there are 30 chapters from the textbook. I put all the chapters up for you. We will be going through chapters from chapters 15 to 30 in this class. And if you want to look back to the earlier chapters, you can. A lot of the information I'm giving you today in this lecture here comes from chapters 1 through 4. And I went ahead and put up 1 through 3 in your module as optional readings. You don't have to read them, but you might skim through them, especially if there's something in our lecture here today that makes it sound like you're a little bit interested in it. One of the things also to note, the video that you're going to be seeing for our next bit on chapter 15 and 16, which is on the sun, I've taken the two chapters and put them together. That's actually the last lecture for 101. It's the first lecture for 102. So you will hear me when I'm in that lecture talking about it being the last video in the last lecture, because I just sort of lifted that up and put it in our class. So now you know. So now don't be surprised when you hear that, because it was just I was thinking of re-editing the beginning, and I thought, no, I'll just explain it in this video. So there you are. That's the explanation. The background I have here is Kirkwood Observatory, which is on the IU campus in Bloomington. Under normal circumstances, the Kirkwood Observatory is open on Wednesday evenings from spring break, which is in March, until Thanksgiving in November, for open houses and looking at the sky. Right now, the university is closed, so it is closed as well. But if you ever make it to Bloomington and can stop by on a Wednesday evening, it's a great place to start. And it taps into the idea of the history of astronomy, which is part of what we're going to be talking about here in this particular Zoom. I'm going to guess that this Zoom is going to last a little bit more than an hour, so either make yourself comfortable or plan to watch it in chunks. Without any further ado, let me start the screen sharing here and see if I can figure out how we're supposed to do this. Okay, it looks like we're sharing the screen. What I'm going to be doing, you'll see me sort of up in the corner. That's me in the corner, losing my religion. But I'm going to go through our slideshow here. If I can find where it says slideshow, play from start. Okay, and then I'm just going to talk a little bit about the different kinds of things. In the history of astronomy, astronomy is actually one of the oldest sciences there are. It's also one of the most new and advanced kinds of sciences that there is. But one of the things that we see is that people have been fascinated by the patterns that we see in the sky. From the earliest rumblings of history and even prehistorical things that we see tell us that they were aware of the patterns of the sun, the moon, the planets, and various other things that may have happened along the way. We have ancient monuments to that. We have modern monuments to that. If you've seen the movie Contact with Jodie Foster and Matthew McConaughey, was based on a Carl Sagan novel. This place here, the Very Large Array in New Mexico, is featured in that. Many of the astronomical places that we have in the world today are in fact monumental. They are huge. And if you think of the NASA space complex where those giant rockets take off, or you think about the hilltop and mountaintop facilities around the world for astronomy, we've got quite a number of those things. But it just speaks to the creativity of the human mind and the way in which we have been curious about the universe in which we live for a very long time. When we talk about astronomy, and it's not astrology, if you keep calling it astrology, I will hunt you down and I will change your grade. So astronomy is a science. Astrology is not. Astrology is closer to a religion. And we'll talk a little bit more about that maybe later in the semester. We talk about the sun and the planets. That's mostly 101. That's mostly the 101 class. Of course, that's closer to home, so we know a little bit more about that in detail. We've actually been to some of those places, either live in person like the moon, or with robotic different kinds of landers and orbiting probes and flyby probes. We look at the stars and galaxies. That's where we jump off here in our class. Then we see the galaxies cluster together in groups and groups and groups. We'll be looking at the idea of life outside of our solar system and outside even of our galaxy, perhaps. And when we use the word cosmology, that's a big word for all that is and all that was and all that ever will be. It talks about time and space warping and all sorts of fun stuff. And we will definitely get into that later in the semester. We think about how long we've had in history to be looking at things. Stonehenge is a place that in many ways is one of the earliest astronomical observatories that we have. It's a lot of stones that are set up to catch the sun and the pattern of the sun in different ways. But that was thousands of years ago. And we can sort of see how long it's taken, if we look at this time chart here, how long it's taken for us to get to the Hubble. But it's really been just in the last 500 years that what we know about the universe has really come alive in terms of how things work. But that's not that many generations. We've only had 25 or 200 generations, if you think about it as being roughly 25 years each to get from there to here. Your book talks about orders of magnitude, and I will show you a couple of videos along the way that play on this idea. If you sort of think about us human beings as sort of a 1, we can get larger and we can get smaller by adding zeros. This little 0 at the top of a 10 here is an exponent. 10 to the 0 power is 1. And we're closer to 1 meter, 1 yard tall. If you're thinking, I'm not 1 yard tall, I'm 2 yards tall, I'm 6'2". But I'm closer to 1 than I am to 10. I'm closer to being 3 feet tall than I am to being 60 feet tall. So we can think of ourselves as 1. By the time we add 6 zeros, that's a whole planet. By the time we add 9 more zeros, that's how large the sun is. Or 9 zeros, sorry, not 9 more. By the time we get up to 13 zeros, we're talking about the entire solar system. And by the time we get up to 24, we're talking about the whole universe. The whole universe, from us to the whole universe, is simply 24 steps. If you think about walking up the steps 2, 3 stories, that's it. If each of those is a larger by the scale of 10, an order of magnitude, we only have to go 24 steps before that's the entire universe. If we get smaller and smaller and smaller, we only have to go down 15 steps. We only have to go basically 1.5 stories down before we get to the smallest things that we can perceive and measure along the way. And we'll talk about some of those things as well along the way. This is scientific notation when we're using exponents. So rather than writing 5 billion, as you see here, we would say 5 times 10 to the 9th. There are 9 zeros there. 1,000 is 7.5, or it's 7,500 when we're talking about thousands here. 7.5 times 10 to the 3. That would mean we would move this decimal point sort of 1, 2, 3 points over. And we can also do that with our negatives going on the other side of the decimal point, so that we don't have to have 0.00000001. We can say 10 to the -6th, and that works along the way. Some things to keep in mind. We are 1 AU away from the sun. That's an astronomical unit. That is about 93 million miles. That's rounding up here, 92.8. That's an approximation, because in fact, sometimes we're closer, sometimes we're further away. You convert that to meters, we're about 150 million meters away. Again, that's rounding up from this. Mostly what we'll be dealing with in this class will be light years. And that is the distance light travels in a year. It sounds like it's a measurement of time, but in fact, it's a distance. It's how far the light's gone in 1 year. And you can see how many meters, a meter is roughly a yard. So think about that. It's 9 times 10 to the 15th. It's 6 trillion miles. It's a long, long, long way. So rather than write out all of that, we say a light year. Light goes along at 186,000 miles, sorry, per second, or 300,000 kilometers, or 300 million meters per second. So that's a long, 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 long way there. When we're looking at sciences are born out of curiosity. Oh, by the way, going back to that other place, these are good numbers to remember and memorize. 1 AU is 93 million miles, 1 light year is 6 trillion miles, speed of light is 186,000 miles per second. Those are good things to just sort of know, have it in your head. People have been doing science in different ways, usually born out of curiosity. What makes this stuff blue? What makes this stuff purple? What makes this stuff green? I mean, all of these different kinds of things are useful if we understand how to get from something to something else. How can we grow better plants? How can we grow better animals? How can we make the world a better place? How can we change different things into useful objects? These actually have to start with science. Sometimes science is lucky and doesn't quite know what it's doing. And sometimes we find out the theory before what we do, and sometimes we find out what we're doing and then find a theory to fit it. So either way works in different ways. It just depends upon the historical situation. But science is a process. It's not just a bunch of facts. You have to actually put them together so that they mean something. It's also not just an opinion. You're observing something. Hey, the sun comes up every day and it goes down every night. So you form a hypothesis. That hypothesis says, hey, the sun is going around us. So we try to confirm that, or we try to figure out if it's wrong. If it's right, and for many thousands of years, people thought it was perfectly right. Yes, and it seemed to confirm itself every day. But eventually, we figured out that there are other things that are out there moving in a way that correspond to the way the sun is moving. And especially when we got off the planet with rockets and other things, we're like, okay, yeah, we're going around it rather than it going around us. Also, we're spinning. So there came at a time experiments that failed to confirm that the sun is going around us. So we had to come up with a new hypothesis and a new experiment for that. So that's how science works. We can use a system that may not be perfect, but it explains the situation that we have until we reach a point where it no longer explains what we have, and then we have to come up with new theories. We have to have new hypotheses. But a theory is not just an opinion, and not every opinion is worth every other opinion. My plumber is a very smart guy. My attorney is a very smart guy. My doctor is a very smart guy. I'm not going to go to my doctor for plumbing advice. Well, maybe heart plumbing. I'm not going to go to my lawyer for plumbing advice. I'm not going to go to my plumber for medical advice or legal advice, because they know what they know, and they might have opinions on the other things, and I might even listen to their opinions on other things. Well, you shouldn't use that kind of tubing. You shouldn't use that kind of document. But I'm going to go with the experts. Experts are not to be sort of poo-pooed just because you have a different opinion or they have a different opinion. Usually people are experts for a reason, and especially in science, that's true. Sometimes we find things by chance. The discovery of penicillin, for example, was discovered by accident. Discovery of X-rays was discovered more or less by accident as well. Then we take what we discover and we put them to practical, sometimes as in penicillin, to really wonderful uses along the way. But an observation is you're seeing something. Now you can set up particular observations. That's what science also tries to do. You try to figure out how to watch something in the best possible way. You also don't want to watch something in a way that changes what you're watching, because that creates another kind of problem. But once you have an observation, it's like, well, that flower always turns purple. That one over there always turns red. You might figure out a reason for that. Then especially if you splice them together, what happens? People who grow roses often will have things that happen along that way. They'll experiment, because you'll say, okay, now if I take this and I take this and I cross them, will something happen? Will the red show up? Will the purple show up? Will they blend together? Will it become mottled and changed? So you test it. And then you try to put the theory that you had, well, I think this will all turn red, this will all turn yellow. We can do different kinds of tests as well. Who has blue eyes, who has brown eyes, who has green eyes, who has gray eyes. There are genetics that are involved in that. We have what are called dominant features and recessive features. And those kinds of things require experimentation too. When we're looking at corn, you're here in Indiana, there's more than corn in Indiana, but guess what? There's corn in Indiana. That ear of corn that you get that's wonderful and delicious and all of that, if you go back a couple of thousand years, it was just this thing called teosinte, and it only had a few kernels, and it was a really tiny kind of stalk. It's through successive growth and testing and experimenting and figuring out which ones are better and which ones are not that we have different types along the way. So that's confirmation or not. If it doesn't work, you throw the hypothesis out. You figure out, okay, this isn't working, this isn't working. When we figure out, okay, the comets are actually closer to the Earth or further away from the Earth, the moon is closer, it's further, the sun is closer or further, the things are going faster or slower. We have to explain what's working, and when the old theories don't work, we get rid of them along the way. So a theory has testing. A theory has something happening that supports it. Not all beliefs and opinions are scientific. This is one of the issues when we're dealing with religion, for example. A lot of stuff in religion may be true, but it's not scientifically true. Just as things in art or poetry or music or other things might be true, but they won't be scientifically true. So watch when people are using the word true, how they're using that word along the way. But this century in particular, this 20th century, we've only been in the sky in terms of planes and spacecraft and other things for about a century. We've only been looking at things in terms of radio waves and microwaves and X-rays and gamma rays and other things for about a century, maybe even less for some of those things. So we keep finding more and more and more things. This picture here of the Earth above the moon as the astronauts were going around the moon, this is often called Earthrise. As the probe was going over, it took this picture. There are millions of people alive today in this country who were here before that picture was taken. This is still new to them. This picture is, I mean, we've got, in fact, everyone today over 65 on Social Security was alive before this picture was taken. It's amazing. It is simply amazing, the kinds of things that we have found. And as we have gotten better and better at our telescopes and better at our observation possibilities, we find these wondrous things called nebulae and these fascinating things called galaxies. In fact, this is the 100th anniversary of the year of what was called the Great Debate on whether these things were inside our galaxy or outside. Only 100 years ago, a lot of people thought there was just one galaxy and we're it. As we try and figure out where these things are, we'll explore how we fit into everything that's out there. But a couple of things to keep in mind: we're in motion, we're moving around the way, and we're moving at an angle. Our planet is tilted as it goes around the sun. And as it goes around the sun, sometimes the north is tilted more towards the sun, and sometimes it's tilted away from the sun. That's because as it goes around, it's tilted in the same direction. But let's see, what can we use for a sun here? Do I have something that can be a sun? Can we see this? Nope, let's see, this wants to disappear. There we go, nope. So there we go. It's tilted away. So, well, great, okay, never mind. I'm trying to do something here and it just doesn't want to work. Notice our graphic down here. Let's go back to the graphic down here. See, sometimes we're pointed away here in the north from the sun. That's our winter because we're pointed away. We're getting less sun as we spin around. When we're in the summer, as we are right now, we're aiming towards the sun, so we've got more daylight. Here we have more night. Then halfway between, we have our equinox days, where it's an equal day and equal night everywhere on the planet. Notice when we're tilted away from the sun, the southern hemisphere is tilted towards the sun. When it's winter here, it's summer in Australia. When it's summer here, it's winter in Australia. So we have this axis of rotation. We're spinning around at an angle to what would be perpendicular to our orbit. And it's because we've got that angle that we have seasons. If we were straight up and down, we don't have any seasons. Venus does not have seasons. It's not tilted. Jupiter doesn't have any seasons. It's not tilted. Mars is tilted like us. It has seasons. But what that means is sometimes the sun is higher in the sky. You may notice that if you go outside and look at the sun, don't look directly at the sun. But if you look up at the sun, you have to look higher than in the winter, where you're going to look lower. You may have a window in your house where sometimes the sun seems to be really right in it and other times it's not. That's because as we tilt a little bit more and a little bit less towards the sun over time, that is going to change the angle of incidence. So in the summer, the sun is higher. In the winter, it's lower. And that's what gives us our seasons along the way. People in ancient astronomy figured this out. That's what Stonehenge is all about. We've also got cycles of the moon. How many of you notice sometimes we have a full moon, sometimes we have a new moon, sometimes we have a quarter moon, and that repeats over and over and over again? People figured that out and they marked them with stones. This is a stone circle for the moon. This is a stone circle at Stonehenge for the sun. But people have been recounting these things and eventually began to write down the patterns. That was important not just to know on a daily basis, but also on a seasonal basis, because hunting and gathering was important. The animals would migrate north and south, or they would migrate away from certain areas and towards certain areas. If you lived on that, you had to follow the animals. It would be helpful to know in the sky when they're planning to move. If you need to plant things, if you need to grow things, if you need to know when the seasons are right for that, you need to follow things along. So that developed into language about patterns, and that's really what mathematics is. Mathematics is a language about patterns. This developed into a more formal structure where, especially in the Greek philosophy system, we had specific people. Thales of Miletus, that's pronounced Thales here, was one of the earliest persons to predict a solar eclipse. In fact, he's reputed to be the first person to predict a solar eclipse. And he did so because he figured out they happen on a pattern, just like the sun coming up and going down every day, and sometimes being higher and lower in the sky every year. The seasons can be predicted, and the solar eclipses and the lunar eclipses can be predicted. All of this could be understood rationally. The sun isn't going behind the moon because the gods are upset for 5 minutes. He said this is a predictable thing that can happen. Pythagoras said, oh, well, we can put math to this. Plato said, well, in fact, we can put everything to math. And then Aristotle fleshed out things quite a bit more. I won't go too much into all of this. I'll let you read this on your own. But this was a relatively slow development. This took hundreds of years, just these 4 guys right here. But what happened was people were still doing their experimentation based on observation. And the thing is, you can't experiment too much off the planet. So you have to improvise. And one of the ways you improvise is you do thought experiments. One of the thought experiments that held true for a long time was Ptolemy's thought experiment. He looked and mapped out where all of the planets were, and he figured out that they need to be going around the Earth, but if they're going around the Earth, like the sun and the moon, they need to be doing these little loop-de-loops, what we call retrograde loops or epicycles, because they didn't always match up. They were not obviously going around in a perfect circle. Sometimes they seemed to slow down and go backwards and go forwards. So he put these little loop-de-loops as everything was going around the Earth. And this worked probably 90–95% okay. But the longer it worked, it's sort of like a clock that's slow. The longer it goes, the more and more and more slow it becomes. That was happening here. For 1,500 years, people thought this was a good system, but it kept making more and more and more mistakes. This was true in Europe. This was also true in the expanding Muslim empire. We often forget that when the Europeans went into what we sometimes call the Dark Ages, the Muslim empire was having a golden age, and there are a lot of things that we still have today that are because they were preserved during that time, including the use of numbers like this, 500 and 14th and 15th and other kinds of things. Those are called Arabic numerals. The weird thing is they actually come from India, but they come to us through the Arabic tradition. Otherwise, we might all be using Roman numerals today, and that would be a real mess. Not least of which is because the Romans didn't have the number 0. So, but as I mentioned, eventually things came to a head in that they couldn't figure out how to add all of these loop-de-loops to make the system work. One of the first persons to really put that all together was a guy named Copernicus. Copernicus wrote a book in the year 1543, and in 1543 he said, everything's going around the sun, except for the moon, which is still going around us. They didn't know about moons around other planets back then. There weren't any telescopes. But he believed that everything was going around the sun in a perfect circle. It made more sense than the loop-de-loops, but it actually wasn't that much better in terms of predicting where things were going to be in the sky, because in fact, it was still a little bit off. One of the things you may notice if you look at the planets and watch them on a regular basis going through the sky is that they will go through the sky and then they'll stop and they'll go backwards and then they'll go forwards again. That's called retrograde motion. And here in this diagram here, we can see why. It's just like a NASCAR race. It's just like an IndyCar race. If you're inside and you have someone going on the outside, if you're going a little bit faster on the inside, the guys on the outside will look like they're going backward. If you've ever watched a dash cam from one of those races, and you can see the cars on the other side, some of them seem to be going backwards. They're not going backwards. They're going 150, 180, 200 miles an hour. But the dash cam is going faster, which is why they look like they're going slower. That's what happens here. The Earth is going faster than Mars. So as Earth goes around and we're looking at Mars, it looks like it's going backwards. It's being lapped until we get around the curve and it gets around the curve and it seems to be going forwards again. That's true for all of the outer planets. But one of the proofs that Copernicus said, if we could actually see Venus close enough, because people had figured out Venus is actually pretty close. It's closer to us than Mars, it's closer to us than Jupiter, Saturn, it's close. So, but it's not close enough for us to see with the naked eye what we need to see. If Venus is going around in this loop-de-loop closer to us than the sun, then look at what we see here. We only see portions of Venus in the light. The rest is dark. Whereas if it's going around the sun, there's sometimes it's going to be full, sometimes a quarter, sometimes new, just like the sun, like the moon. So this was 1543. We had to wait until 1610, 1611 for Galileo to come along and say, see, I'm looking. In between those two things, in between Copernicus, who actually wrote his book and then died the same year, and Galileo picking up his telescope and going to work in 1610, 1611, we got two guys who are very important in astronomy. This is one of them. This guy is named Tycho Brahe. We often call him Tycho. Most of the time we refer to people as by their last name, but Tycho is sort of like Cher. You just, Cher is Cher. You don't need her last name. Tycho, you don't need his last name. But he was perhaps the greatest observational astronomer in history. He lived before telescopes, but the measurements he took in the sky were so good that for 100 years or more after he died, they were still using his measurements rather than the telescope measurements. He was a great, great observational astronomer who left most of his work to a guy named Kepler. Kepler came along and took all of that data and put the mathematical formulas onto it to make it work. So we have a division of labors, and that's still true to this day. There are a lot of people who are like Tycho, who will go out and look at the sky and take pictures and do the observations. Then there are a lot of people like Kepler who will go out and crunch the numbers and do the data and do the mathematics. Both are doing astronomy, both are doing astrophysics in many ways as important to each other. But what happened, of course, is that as they were putting all of this together, Galileo back in Italy was beginning to invent new things to help along the way. And one of the inventions he happened upon was the telescope. He did not invent the telescope, but he was a good enough craftsman that when he heard about it, he made his own. He didn't have to buy one. He made his own from the description. And he made his first one in 1609, we believe. And he started looking up at the sky and taking measurements 1610, 1611. One of the first things he did was he looked at Venus, and he saw all those phases that Copernicus, remember him, had said you could see, and that would prove it was going around the sun. He looked at the moon, and he saw that it was not smooth. Now, Aristotle, 1600, 17, 1800 years earlier, had said everything in the heavens, we still use that word today sometimes, are perfect. Smooth, had to be smooth. Nope, it's pockmarked, it's got acne, there are all sorts of problems with it. But here's was the real clincher. He looked at Jupiter, and you can do this on your own. If you've got a pair of binoculars, 10 by 50 binoculars will do it for you. You can see the 4 moons, now called Galilean moons. You look at Jupiter and it'll break apart into dots. And what Galileo saw was that there were dots that were moving around Jupiter. So say my head's Jupiter, and there would be 2 dots over here and 2 dots over here. And then a few days later, there would be 1 dot over here and 2 dots over here. And then a few days later, there would be 1 dot here and no other dot is in front of or behind, so you wouldn't see it. As they're going around, sometimes they're in front, sometimes they're behind. Sometimes all 4 of them are on the sides. If you sort of look here, you see we've got all 4. Look here, and we've got all 4 in a different pattern. But one of the things he noticed was we've got 2 and 1 here. We've got 1 and 2 here. We've got 2 and 1 here. We've got 2 here. Where's the 1? Uh-oh. Here's 2 and 1 here. There's 2 and 1 here. He noticed that 3 out of 4 had a particular pattern that only lasted a week. One of them was zipping around every 7 days. See, our moon takes about a month to go around. This one took a week to go around, but there was another one that took 3.5 days, half a week. And there was another one that took less than 2 days whipping around. These things are all going around Jupiter, back and forth and back and forth. This was the first time in history anyone had ever seen anything going around something other than the Earth. Whoa. If there are things going around Jupiter, then maybe we're going around the sun. So this was confirmation. Now, of course, what happened was he wrote a book. The church read the book and said, why don't you shut the hell up? Literally, that's what they said. They threatened him. Now, I want to be very careful here and let you know. Galileo was in Italy, so the church that I'm talking about here was the Roman Catholic Church. Sometimes when people talk about Galileo and the church telling him to shut up, it becomes an anti-Catholic kind of thing. But here's the thing. In the German areas that were Protestant, and in England that was Protestant at the time, if he had been there doing this, he probably would have been burned at the stake as well. So nobody wanted this. Nobody in religion wanted this because it seemed to make people less important and seemed somehow to make God less important. I don't think that's true at all. I think I can be a Christian. I am a Christian, just so you know. I'm actually a chaplain and an ordained priest, so bless you all. But I'm also an astronomer. One of the interesting things is there are lots of Jesuit priests today who are astronomers. There are lots of people who are ministers who are astronomers and other scientists as well. So before we get sort of too anti-clerical or anti-religious, just remember that's not usually the prevailing outset. But his ideas didn't stop. And a lot of his ideas got published anyway, especially outside countries, in the Netherlands, in Holland in particular, where they didn't have these kinds of rules and censorship. And taking all of this stuff, Copernicus with everything going around the sun, and Kepler with his mapping things out in much more precise ways. The main thing Kepler did was he said things aren't going around in a perfect circle. And once they got that idea enshrined, hey, everything started fitting. There it is, there it is, there it is, there it is. Tycho's data worked and Galileo's observations worked. Came to a guy named Newton who said, haha, now I can explain things. We're not just saying what's out there, we're saying why it is. And he set up what we call the laws of motion. Now his first law is in many ways a plagiarism of Galileo. Back then, borrowing ideas and borrowing words were a little more flexible than they are today. But this is inertia. What he figured out was The natural motion of things tends to be in a straight line. If you're not going in a straight line, there's a force acting on you. That's what's pulling you around, pulling you down. The Earth is not going in a straight line in space, it's going around the sun because the force of the gravity of the sun is acting on the Earth. The moon isn't going in a straight line because the force of the gravity of the Earth is acting on it. If you throw a ball, it's going to curve. It's going to curve up and back down, or it's just going to curve down. But it's not going to go straight because the Earth's gravity has an effect on it along the way. And you can throw it up higher and higher and higher, and guess what? It still curves back down unless you have enough oomph to counteract the force. That's what rocket ships do along the way. And rocket ships then have to figure out the forces that are involved. And this comes up to the second law of Newton. Forces equal how much stuff is in something with the acceleration. Now, acceleration can be both just movement as well as motion in different directions. So we multiply the mass times acceleration, that gives us the force. If you have something really big, it doesn't have to have a lot of acceleration to have a big force if it falls on you, for example. If a feather falls on me, no worries, there's not a lot of mass there. If a bowling ball or a Zamboni machine falls on my head, I'm in trouble, even if it's not falling very hard or falling very fast, because it doesn't need that. The acceleration is the smaller thing, the mass is the larger thing. Sometimes we have large mass and acceleration here. When the space shuttle was a thing and we were launching that, notice this big orange tanker here, that's just a gas can. There's one of these, this is called the solid rocket booster. There's one other one on the other side. Those are filled with fuel, that's all they are. They're gas tanks and an engine at the bottom, and then a gas tank in the orange thing and an engine at the bottom of the shuttle here. And within just a couple of minutes, they're out of fuel because it takes, on average, 740 pounds of fuel to get 1 pound of space shuttle up beyond the Earth's gravity. It takes a lot. And for every force that's out there, there's an equal and opposite reactive force. If that force lifting the shuttle off wasn't being reacted against, then it would just dig a hole and sink. Right now I'm sitting here in my chair and I am pushing down with 200 pounds of force because that's how much I weigh. The chair, thankfully, is pushing up with 200 pounds of force. If it were pushing up with more, I'd be catapulted away. If it were pushing up with less, I'd be falling down. So we have that law too. So those are 3 laws of motion. Those will be important for us when we're talking about gravity later. And this is one of the ways in which it's important to remember how the gravity works. Everything that's massive in the universe has gravity. Anything that has mass, even if it's just a tiny mass, if it's a big mass, everything has gravity. The more mass you have, the more gravity you have. That's how it works. So the moon is smaller than the Earth, it has less gravity. The Earth is smaller than the sun, it has less gravity. But it's not just how much mass, it's how much distance as well. If you have 2 things that are here, they're more attracted to each other than 2 things that are here, and more attracted to each other than 2 things that are here. The further away things are, the less attractive they are, and they are less attractive to each other based on a particular equation. I'm trying to see, okay, here. I want to annotate a couple of things here, so forgive me if I'm sort of pausing for a moment. This equation here, notice this equation here. This is the force equation that's happening. This Fg here just means the force of gravity, so don't let it scare you. This G here is called the gravitational constant. It's just a number to make the rest of the equation balance out. Then we have our M1, that's here, and we have our M2, that's here, and we have our distance, R. That's it. So we have M1 and M2 multiplied together, divided by R, the distance squared. And the reason why it's divided by squared is because gravity falls off really quickly. If it's 2 times as far away, it's 1/4 as attractive. If it's 3 times as far away, it's only 1/9 as attractive. If it's 10 times as far away, it's 1/100th as attractive, because 1/2 the distance here, if it's 2 times as far away, that's 2 times 2, that's 1/4. That's what this equation is here. Notice they're less attractive. By the time we keep going down further and further and further, the gravity doesn't turn into 0, but the further away that shuttle gets from the Earth, the less gravity there is. It's not that there's no gravity. After all, when the rocket ships went to the moon, they reach a point where, hey, there's no more gravity, right? Wrong. There is gravity. Otherwise, the moon would have flown off on its own a long time ago. There's gravity from the Earth all the way to the moon. But what was happening inside that rocket ship is that they're in a free fall kind of situation where they don't have the gravitational sense. Also, they're so far away, there's less and less and less of it as they're going forward. You actually weigh less on the second floor than you do on the first floor of any building, which is rather interesting. I think that's it for this particular lecture. One of the things you'll also want to do this week, of course, is now go to the lecture on chapter 15 and 16, which is on the sun. We're going to start with the star that's closest to us. And remember what I said before, that lecture is the last lecture of the 101 class. And that's what I recorded it originally for. So the wording at the beginning will be in reference to that. So don't be thrown off by that along the way. And I think that's probably all I need to report here. Be sure to watch a couple of videos that I will have in the announcements on the syllabus and on a few other kinds of things coming up here. But I look forward to being with you through the rest of our class. Thanks.